Hello and welcome to this topic, the application of differentials, linear approximation. We have just seen how derivatives allow us to compare related quantities that are changing over time. In this section, we examine another application of derivatives, the ability to approximate functions locally by linear functions. Linear functions are the easiest function with which to work, so they provide a useful tool for approximating function values. Consider a function f that is differentiable at a point x is equal to a. Recall that the tangent line to the graph of f at a is given by the equation y is equal to f of a plus f prime a times x minus a. In general, for a differential function f, the equation of the tangent line to f at x is a can be used to approximate f of x for x near a. Therefore, we can write f of x is approximately equal to f of a plus f prime a times x minus a for x near a. We call the linear function Lx is equal to f of a plus f prime a times x minus a the linear approximation, or tangent line approximation of f at x is a. Here we have the idea of local linear. Look at these graphs. The tangent line to the graph of f is x squared at point 1, 1 is a graph of y is equal to 2x minus 1. When we magnify the graph, we will see the curve of f is equal to x squared is getting closer and closer to the line of y is 2x minus 1. So when we magnify it, it's getting closer and closer. But not all functions are locally linear. Now look at this one. This function is named as Weierstrass function. In mathematics, the Weierstrass function is an example of a real-valued function that is continuous everywhere but differentiable nowhere. It is named after its discoverer, Carl Weierstrass, a German mathematician who is often cited as the father of modern analysis. From this graph, we can see that no matter how we magnify it, it couldn't be linear. The linear approximations can be used to estimate function values. They can also be used to estimate the amount of function value changes as a result of small changes in the input. To discuss this more formally, we define a related concept, differentials. Differentials provide us with a way of estimating the amount of function changes as a result of a small change in input values. When we first look at derivatives, we use the Leibniz notation dy over dx to represent the derivative of y with respect to x. Although we use the expression dy and dx in this notation, they did not have meaning on their own. Here we are going to see a meaning to the expression dy and dx. Suppose y is f of x is a differentiable function. L is a tangent line to the graph of f at point A. Let dx is the increment of x. We can find delta y in the graph, which means the increment of y with x increasing to x plus dx. To approximate delta y, we define the dependent variable dy by dy is f prime x times dx. delta y is approximately equal to dy with the error. The error is higher order infinitesimal of delta x. Or we write it as higher order infinitesimal of delta x, like this. So we have delta y is equal to dy plus the higher order infinitesimal of delta x. It is important to notice that dy is a function of both x and dx. The expressions dy and dx are called differentials. We can divide both sides by dx, which yields like dy over dx is f prime x. This is a familiar expression we have used to denote a derivative. Now let's see one example. Suppose you need good approximation to square root of 4.2, but your calculator has died. So what might you do? Jordanson, could you tell us?
Yes, consider the graph of square root of x. When x changes from 4 to 4.2, square root of x changes from square root of 4 to 2 to approximately square root of 4 plus dy. Now dy equals to 1 over 2 times the square root of x times dx. We plug in x equals 4 and dx equals 0.2, then dy equals 0.05. So the square root of 4.2 approximately equals the square root of 4 plus dy, which equals 2.05.
Alright, thank you very much, Johnson. Now let's see what the calculator gives us. Is that the same as Johnson's answer? Now let's see that. So we open the calculator and input 4.2 and take the square root. Then we will have the answer is about 2.049390. It's very close to 2.05. So the approximate value 2.05 may be compared to the true values. So it's very nice approximation, isn't it? Now let's do next example. Example 2. Use differential to approximate the increase in the area of a circle when its radius increases from 3 inches to 3.025 inches. Alright, please take 1 minute to think about it. Jack, could you tell us how to solve that?
Okay. The area of a circle is given by A equal pi r squared. We may approximate the change that A by the differential dA, where dA equals 2 pi r dr. At r equals 3 and the dr equal delta r, that is 0.025. So dA approximately equals 0.471.
Alright, thank you so much, Jack. So Jack found that the increment of area is about 0.471. Today we learned the basic idea of approximation, and we will discuss more interesting examples next time. So that's all for this section. I'm looking forward to seeing you next class. Thank you.